Hey Dr. Ko, let's talk about some tanks. So we've got tank 1 here, tank 2 here. They both have a water level. Tank 1 will be H1 and tank 2 will be H2. Tank 1 is a flow in, Q1. Tank 1 to 2, the flow is Q12. And tank 2 has a flow out, Q2. We want to find the governing differential equation for the liquid heights in tanks 1 and 2. To do this, we first start out with volume. The volume of tank 1 will be H1 times A1, which is the cross-sectional area of the tank. Both tanks have that. Now we want to get the, now we'll get, or we will see how this changes over time. So we have the change in volume as denoted here. We could set that equal to the flow in minus the flow out, which would be Q1 minus Q2. After we arrange this, we can get dH1 over dt, which is the change in height of tank 1, equal to the flow in minus the flow out over the cross-sectional area. This also applies to tank 2, where it would be the change in height of tank 2 is equal to the flow in, which in this case is Q12, minus the flow out, which is just Q2, over the area of the cross-sectional area of tank 2. We were also given equations for the flows. Q12 is equal to 0.5 square root of H1 minus H2, and Q2 is equal to 0.25 square root of H2. We can plug those into these equations to get the governing differential equations for the height of each tank. Now we can move on to coding.
Okay, now we get to code. So we're first going to import all of our useful functions. This one is very useful. Now that we have all of our functions imported, we can all right. Now we can move on. Now we're going to define our differential equation in terms of t and y. Our h1 will be y0, and our h2 will be y1. All right. Now we can insert the flow rate. We were given Q12 equal to we're going to say A1, and that's the alpha out in front of the square root, and that's multiplied by the square root of H1 minus H2. Now Q2 flow rate is equal to, that's A2 for alpha 2 times the square root of H2. And we have those. The differential equation for the height of the first tank is equal to, we have the initial, the flow into the tank is Q in into tank 1, Q in of T minus Q 1, 2, and that's all divided by A1 for the cross-sectional area. This QNT is our function of time that we're going to do more with later. Now QH2 is equal to Q12 minus Q2, and that's all over the cross-sectional area of tank 2. Now and return those differential equations, 1 and right, and everything looks good, so we can move on. Now we can plug in our variables. So alpha 1 is 0.5. Alpha 2 is equal to 0.25. The cross-sectional area of tank 1 is equal to 1. And the cross-sectional area of tank 2 is equal to 1.5. So now going on from here, we put the initial height. That's the initial height of tank 1 is 2 meters, and the initial height of tank 2 is 1.5 meters. We're going to say that T end, which is how long our system is going to run, is 100 seconds. And Q in V for the vector is going to equal, it's going to start at 1, it's going to go to 1.5, and then it'll stay at 1.5. Now our Q in T, that's for the time, is going to start at 0, and then it'll stay at 1 for 50 seconds. And then it'll go to 100, which is T end, and it'll go up to 1.5. Now we will finish our Q in, which will be, and we'll use inter P1D. Now that we got this, we can move on to the figure. We want to first solve this IVP, the differential height equation. We want that from 0 to T end. HI for the initial height method. We're going to use the Rada method, and we want the dense output to be true. And now we can continue with the graph. T is going to equal NP lens space 0, T end 100. Solve gonna get our figure in here. Add again. This time we're gonna add the H2. This time we're gonna use Sol1. And our name, this one is H2, so calling it H2. Okay. And now we do figure.show and pray that we did it correctly. And now we get a graph showing the height of tank 1 over time and the height of tank 2 over time. The height of tank 1 increases still, and the height of tank 2 also increases, but at a slower rate. Thank you for listening to me, Dr. Ko.